Welcome to today's lesson on understanding how energy is stored in capacitors and how to calculate it. Capacitors are fundamental components like resistors in many electrical and electronic circuits. We need to understand its energy storage capabilities. I believe that at the end of this lesson, you will be able to derive the formulas surrounding energy stored in a capacitor and also be able to apply them in electric circuits. That said, let's get into class. Let's start with a basic understanding of the capacitor and its capacitance itself. Now, here is a visual diagram reflecting how the capacitor behaves. Now, I have a battery source here supplying voltage to this capacitor. I also have the capacitor having two different plates, the positive plate and the negative plate. As voltage is actually being applied across this capacitor, you will notice that charges continues to be built up and also energy is built up around this system. Now, this is actually a replica of this system in a circuit. I have my positive part. Here is the positive part of the voltage source. Like you can also see in here, is being connected directly to the positive terminal of the capacitor. The negative part of my voltage source is connected to the negative part of the capacitor. Energy and charges are actually being stored on the capacitor. Like you can see here, this is a plate, and as this voltage continues to charge the capacitor, energy is being stored. The energy being stored on this capacitor E, change in this energy level, because this energy is going to start from probably zero, it's going to be the same thing as voltage times a change in Q. Now we know that we said that Q is equals to CV, which implies that V obviously will be the same thing as Q over C. So that I can now say that change in E will be the same thing as Q over C change in Q. Now let's see, to solve for E now, the best thing is to integrate. So on integrating a change in E, I'll also take an integral of a change in Q over C with respect to what? To Q. Now, at this integral, because my plate is being charged from 0, we'll take it from 0 to the final charge of what? Of Q. So that finally, E will be the same thing as C is a constant. I'm going to bring out 1 over C and integrate for Q from 0 to Q with respect to Q. So that E now will be the same thing as 1 over C Q raised to power 2 over 2, which is the same thing as Q squared over C over 2C. Now remember we said that Q is equal to CV, so in place of Q squared, I can replace Q with what? With CV. So that E now is the same thing as the same thing as CV all squared over 2C. Definitely C here will be 1, then one of these C's will go out. I'll still be left with 1C. So that this E is now the same thing as CV squared over 2, which is equals to half CV squared. Let's take some example. Our question says, determine the energy stored in a 3 microfarad capacitor when charged to 400 volts. Remember we said E is the same thing as half CV squared. That will be equals to half times C, which is 3, times 10 to the power minus 6 times 400 all squared. Remember V is 400 volts. So that this is the same thing as half times 3 times 10 raised to the power minus 6 times 400 squared. That will be 16 times 10 raised to the power 4. Now 2 here is 1, 2 in 16 is 8. 8 times 3, that's something as 24. Now times 10 raised to power minus 2. Look at it this way. This is minus 6. Here is 4. From our indices, this is 10 raised to power minus 2. In case you miss our lesson on indices, we'll place a link in the description. We'll place a link up here so that you can access that lesson. Now, energy is measured in joules, so that this is equals to 2 times 10 raised to power 24 times 10 raised to power minus 2 joules. Better put, I can easily relate E now with the same thing as 0.24 joules. Now let's look at the B. The B part of the question says, find also the average power developed if this energy is dissipated in a time of 10 microsecond. Now we're given time of 10 microsecond. We have to find power. Remember that power is the same thing as energy over time. So that this is the same thing as energy. We've gotten our energy to be 0.24 over 10 times 10 raised to the power minus 6. So that this is equals to, now look at it this way. This is just indices. Let's play with indices. This is 0.24 over 10 times 10 raised to the power minus 6. That's 10 raised to the power minus 5. Now when I have my 10 raised to the power minus 5 as a numerator, as a denominator, then I have to bring it up, it becomes positive, which is equal to 0.24 times 10 raised to the power 5. Now 0.24 is the same thing as 24 times 10 raised to the power minus 3, now times 10 raised to the power 5. Sorry, 24 times 10 raised to the power minus 2, minus 3. Now, so that my power dissipated will now be the same thing as 24 times 10 raised to the power 3 watts. Power is measured in watts, which is equals to 24 kilowatts. Now, so you see how we've calculated energy and how we've calculated power. Here is a third example, which I want you to give a try. It says you can pause the video. The question says a 12 microfarad capacitor is required to store 4 joules of energy. Find the PD, that is the potential difference to which the capacitor must be charged. You can pause the video for some minutes and give it a try. Okay, that's it. Now, if the charge on the capacitor C is given as 12 microfarad and the energy stored on it is given as 4 joules, then I should be able to calculate the capacitor. Remember that I should be able to calculate the potential difference. Remember that my energy E is given as half CV squared. So now we're going to do a change of subject formula, and we're going to make V the subject of the formula. In case you missed our lesson where we explain change of subject formula, we'll place a link in the description to help you access that lesson. Now, if E is equal to half CV squared, obviously, if we multiply both sides by 2, 2 times E will be the same thing as CV squared. Let's divide both sides by C. Divide both sides by C. I'll have C at this end cancel C at this end. So 2E over C will be the same thing as what? V squared. Now to solve for V squared and make V the subject of the formula, I'll take a square root of both sides, raised to power half. Here also will be what? Raised to power half. That's the square root sign. So that finally my V is equals to 2E over C raised to power half. So V is the same thing. I can rewrite it this way for convenience. 2E over C. Now my E is 4 joules and my C is 12 microfarad. So that my V is the same thing as the square root of 2 times E, that's times 4 joules, over 12 times 10 raised to power minus 6. 2 here is 1, or rather, let's start with 2 here is 1, 2 in 12 is 6, 2 here is 2, 2 in 6 is 3. So that this is the same thing as the square root of 2 over 3 times 1 over 10 raised to power minus 6. Let's rewrite it. Its indices once more, which is equals to the square root of 2 times 3 for my calculator is something as 0.667 times 10 raised to power 6, which is equals to now the square root of 0.667 times 10 raised to power 3. So that V is equals to the square root of 0.667 for my calculator is the same thing as 0.816 now times 10 raised to power 3 volts. So that the potential difference required is 0.816 times 10 raised to power 3, which is the same thing as 816 volts. With this, I hope you understand how to calculate energy stored across a capacitor and also how to derive the formula. In case you are yet to subscribe to our channel, please do not hesitate to hit the subscribe button. That way you'll be telling YouTube you love what we're doing and you encourage us to do more. Thank you for staying with us and see you in our next lesson.